Hello everyone. In this video, we will continue to examine topic 5, electricity and magnetism in electric fields, and we will continue to focus on the development of the model of charge. In the last video, we discussed some primary experiments that led to the model of charge, and then we discussed aspects of the model of charge. So quickly to reiterate, charge has two species, positive and negative. Like charges repel, unlike charges attract, and the electric force depends on both the quantity of charge and the distance. We know that charge is quantized, so in small discrete units of the elementary charge, and we know that charge is conserved. Okay, again, these experiments, or the experiments that demonstrated this, were conducted significantly later in time, but these form our modern understanding of the model of charge. We also define the net charge as the magnitude of the positive charges minus the magnitude of the negative charges. So, what is happening in experiments numbers 1, 2, and 3? As it turns out, experiment number 2 and experiment number 3 are a little bit easier to explain, so we'll start with those. And it fundamentally begins when, in those experiments, the plastic rod is rubbed with a cloth. If you did this with a comb or in a t-shirt, it's same process for rubbing the comb with the t-shirt, or for that matter, for rubbing the balloon on your head. What happens when the plastic rod is rubbed with the cloth is that electrons, which are small, light, and on the outside of the atoms. Notice the protons are bound to the nucleus in the center of the atom, and they're very difficult to move. And they make up the majority of the mass. So when we think of the comb, we think of the mass of the comb. That is, by a vast majority, the protons and neutrons. So returning to this, when the plastic rod is rubbed with that cloth, those small, light electrons carrying negative charge transfer from the cloth to the rod. And that is what is happening in that process. This is known as frictional charging. And the rod is then net negatively charged. Of note is that it is not obvious at all that the electrons are going from the cloth to the rod. That just happens to be the case here. There's a branch of physics that is concerned with figuring out which direction sort of the electrons would go in a case like this, but that is outside the scope of the syllabus. So take my word for it, in this particular case, the electrons are being transferred from the cloth to the rod. And then, because of the nature of that plastic rod, those electrons just kind of hang out wherever they ended up. So if we look at this diagram here, we can see that the protons are sort of evenly spaced. Those are represented by the pluses. Obviously, there are trillions of them. We represent it here using 4 positive signs. And then those electrons, you can see there's some extra electrons, demonstrating that this rod has a net negative charge, and those electrons are sort of stuck to wherever they ended up. Notice that this would not be true for metal, for reasons we'll discuss later. So we then look at experiment 2. If 2 plastic rods rubbed with a cloth come near each other, then we know that the net negative charge on both rods leads those 2 rods to repel each other. The extra electrons means that both of the rods are net negatively charged. They have extra electrons, and then the electrons repel each other. Notice there are protons in both of the rods, but there are extra electrons. And so the key to deciding whether 2 objects will attract or repel each other depend pretty crucially on the net charge in that region. And the general idea here is that like charges repel. In experiment 3, plastic rubbed with cloth and glass rubbed with silk will attract. Well, this can be explained using the model of charge as well, except now we can infer here that when the glass is rubbed with silk, the electrons are actually leaving the glass and going to the silk. Again, that's not obvious. It just happens to be true. The only thing that would be obvious or would be apparent or discoverable from this experiment is that they must be going in opposite directions. But given that we know that cloth rubbing plastic leads to extra electrons on the plastic, then we can infer that silk rubbing glass will actually remove electrons. And so the glass is now net positively charged. Because the plastic rod is net negatively charged and the glass is net positively charged, those two rods attract because unlike charges attract. Okay? Note that in most electrostatics experiments, we're going to be discussing electron transfer due to frictional charging, and that in solids, frictional charging always involves the electrons transferring because they're small, light, mobile, and on the outside of the atom, and the protons are locked within. In other materials, in melted solids, so liquids, and in aqueous solutions, it is not always the case that it's only the electrons that are moving. And that's important to note for future experiments. All right, so finally, we examine experiment 1, which is a little bit trickier to analyze. Okay, so remember that in experiment 1, a plastic rod rubbed with a cloth attracted little papers. A balloon rubbed on hair will stick to a wall or attract hair. I'm going to use the balloon version just because it's easier to draw little diagrams of pictures of what's going on, but the essence of the explanation will be the same here. We start, as with the first case, where the cloth is rubbing on the balloon, and the balloon then becomes net negatively charged. So again, electrons end up transferred to the balloon, and now the balloon has extra electrons and therefore a net negative charge on the balloon. Okay? And in the second case, all right, we'll see that that balloon is then attracted to the wall. Why is this? Okay? First of all, it's not because the wall is positive. The wall isn't positive. The wall is net neutral. But inside the molecules of the wall, the extra electrons in the balloon can affect the electrons in the molecules of the wall. Although those electrons can't transfer easily, they can rotate a little bit. They can sort of move around their own molecule. And as a result, when you bring that balloon close, okay, you bring the balloon close, the extra net negative electrons on the balloon repel the electrons in the wall. As a result, those electrons all sort of scoot over to the far side, as far away from the balloon as they can get, and still be in their sort of region, in their molecule. This separates the charge so that you get a net positive charge on the wall closer to the balloon and a net negative charge on the wall away from the balloon. This charge separation is known as polarization. So the balloon ends up polarizing the molecules in the wall. And each individual molecule is not terribly polarized, but over a lot of particles in the wall, it adds up. It makes a difference. Because that balloon is not transferring charge to the wall, we say that this process of polarization is by induction. So it the balloon induces polarization in the wall. Now, how does this explain the attraction? Why does the balloon stick to the wall? Well, the key thing to note is that if the negative charges, which are repelled, scoot away from the incoming balloon, then that negatively charged balloon is now closer to the positive charges in the wall than it is to the negative charges in the wall. At least near the balloon. Notice away from the balloon, it's still sort of a random distribution. So near the balloon, the positive charges are closer than the negative charges. So even though the wall is neutral, there is a stronger attractive force between the extra electrons in the balloon and the positive charges in the wall than there is a repulsion between the extra electrons in the balloon and the negative charges in the wall. I'm going to say that again. There is a stronger attraction between the net negatively charged balloon, the extra electrons on the balloon, and the positive charges on the wall, which could not move. They're still where they are. Than there is between the net negatively charged balloon and the negative charges in the wall, those electrons which have all scooted over because of the repulsion between the extra electrons in the balloon and the negative charges in the wall. The result is that the balloon is then net attracted to the wall. So even though these electrons are being repelled by the electrons in the wall individually, these electrons are also closer to the protons. And as a result, there's a net attraction. That's why fundamentally, charged objects will be attracted to neutral objects. They are not as attracted to neutral objects as they would be to an object with opposite charge, but they are attracted to neutral objects. And that explains why that charged rod will attract little papers, and why the balloon that's charged will attract hair. Little papers and hair are very light, and so it's easy to see what's going on there.